Welcome to this episode of Conversations About Geology. I am your host, Professor Gilbert Bernhardt, and today we are going to discuss how the Mid-Holocene Climatic Optimum, known as MHCO, changed the rivers of Texas. When geologists talk about the Mid-Holocene Climatic Optimum, it's often described in just a few words: warmer and drier. But what did that mean on the ground? And more specifically, what did it mean for the streams and rivers of Texas? Did rivers dry up? Did floods stop? Or did rivers simply behave differently? To answer that, we need to think less about rainfall totals and more about effective moisture. The Mid-Holocene Climatic Optimum occurred roughly between 8,000 and 4,000 years ago during the middle part of the Holocene. It's also known as the altithermal or hypsithermal. In Texas, this interval is better understood as a time of increased temperature and variability rather than uniform drought. The primary cause of the Mid-Holocene Climatic Optimum was orbital forcing, specifically precession. During this time, northern hemisphere summers occurred closer to the sun, increasing summer solar energy. That meant hotter summers even if rainfall did not change significantly. Earth's axis of rotation undergoes precession on a cycle of approximately 26,000 years. At the same time, the orientation of Earth's elliptical orbit slowly rotates. When these two motions are combined, they produce a 21,000-year cycle in seasonal insolation. During the early to middle Holocene, northern hemisphere summers occurred closer to perihelion, increasing the amount of solar energy received during the summer months. Summer insolation did not peak briefly. It remained near its maximum for several thousand years. This prolonged period of elevated summer insolation produced the Mid-Holocene Climatic Optimum. The MHCO was therefore not a short-lived event, but a climatic plateau driven by sustained orbital geometry rather than abrupt forcing. This brings us to the key concept of effective moisture. Effective moisture is the balance between rainfall and losses from evaporation and transpiration. During the MHCO, higher temperatures increased evapotranspiration, leaving less water stored in soils and groundwater, and therefore less water available to sustain stream flow. It's not how much rain falls, it's how much water stays. Before the Mid-Holocene Climatic Optimum, during the early Holocene, many Texas streams experienced more sustained flow and valley filling. During the MHCO, flood became episodic. Streams were quiet for long periods, punctuated by short, high-magnitude flood events. Episodic describes how streams flowed during the Mid-Holocene. Long, quiet intervals punctuated by rare floods, without implying that rivers became fully ephemeral. Most geomorphic work, such as channel migration, cutoffs, and overbank sedimentation, occurred during these relatively rare floods, rather than through continuous flow. Texas streams did not shut down during the MHCO. Instead, Baseflow weakened and floods became less frequent but more geomorphically effective. Most channel changes happened during rare, intense floods. These images represent the conditions of many Texas rivers during much of the Mid-Holocene Climatic Optimum. Base flow was lower and channels were stable for long periods. Most of the geomorphic work, such as bank erosion, cutoffs, and floodplain reworking, occurred not under these quiet conditions but during rare, high-magnitude floods. Texas rivers did not disappear during the Mid-Holocene Climatic Optimum. Instead, they changed their rhythm. Most major Texas rivers likely retained some base flow during the Mid-Holocene Climatic Optimum, but base flow was weaker than today. Drier conditions reduced effective moisture and lowered groundwater levels, so streams flowed less consistently. When intense storms did occur, dry soils and limited storage produced high-magnitude runoff, increasing stream competence and causing most channel change to occur during rare flood events. Reduced effective moisture during the MHCO also influenced floodplain development. During extended dry intervals, floodplains became stable surfaces. Soil formed and vegetation stabilized banks. When rare high-magnitude floods occurred, these stable surfaces were rapidly buried by fine-grained sediment, producing the alternation of buried soils and flood deposits commonly observed in Texas floodplains. This image shows a modern analog for oxbow lake formation, which helps us understand how oxbows likely behaved during the Mid-Holocene Climatic Optimum. Channel cutoffs still occurred during rare high-magnitude floods, but reduced effective moisture meant that many oxbows were shallow and often seasonal. Rather than remaining permanently water-filled, these basins commonly experienced intermittent water levels and rapid infilling by fine-grained sediment. As a result, long-lived oxbow lakes were probably less common during the MHCO than under modern hydrologic conditions. This schematic summarizes the process we infer for oxbow lakes during the MHCO. Meander cutoffs created shallow oxbow basins, but limited base flow and reduced effective moisture prevented sustained water levels. During quiet intervals, these basins were often dry or only seasonally flooded. When rare intense floods occurred, fine-grained sediment rapidly filled the oxbows, burying organic material and leaving a stratigraphic record of brief aquatic conditions followed by rapid infilling. The expression of the MHCO varied across Texas. The Great Plains and interior regions experienced the strongest reductions in effective moisture, favoring intermittent streams. Central Texas streams were buffered by spring systems, but still showed reduced base flow. Along the Gulf coastal plain, rivers like the Brazos flowed across low-gradient floodplains dominated by fine-grained sedimentation. Across all regions, river behavior reflected variability, not absence. The Mid-Holocene Climatic Optimum ended gradually as orbital geometry shifted and summer insolation declined. As summer insolation declined, temperatures moderated, evaporation decreased, and effective moisture increased. Late Holocene river systems became more dynamic, with increased lateral migration and more sustained discharge, conditions closer to those observed today. Streams flowed less often, but when they did, they mattered more. Understanding this shift in river rhythm is essential for interpreting floodplain stratigraphy, soil development, oxbow formation, and archaeological preservation across Texas. The rivers we see today carry the imprint of this Mid-Holocene climatic legacy, written clearly in sediment, soils, and landform. This video was written, produced, and hosted by Professor Gilbert Bernhardt. The music for the video is Reverie, composed by Claude Debussy and performed by Simone Renzi.